This topic shows how to organize components of a large C program in a way that reflects modern object-oriented, or OO, design. This organization is often used in well-designed C programs, and it also provides a vehicle to introduce several C language concepts related to larger code. The example notes for this lecture show a program that uses a linked list to store integers. And in there we have a list.h file, and below it a list.c file. Following the design that you've seen before for C programs, the header file list.h gives the prototypes for the list functions down here, and it gives a list struct type and some other supporting declarations needed by anyone who calls the list functions. List.c gives the actual function definitions, the code. But there's more going on here than just a header and source file pair. Our list has a head pointer, but also a count of how many nodes are in the list, and an @ pointer that'll be used by iterator methods that we'll discuss later. Now these are all in the list struct, which illustrates a general pattern, a declaration of a struct to hold all information relevant to some data structure like our list, possibly with supporting types like node, and we'll talk a little bit more about that rather truncated node declaration below. And be clear about the difference, by the way, between the list struct and the node. For each list, no matter how many nodes it has, there'll be just one list struct. Now, in an object-oriented language like Java or C++, one declares a class, which is a sort of augmented struct type, having fields, member data, and also functions, usually called methods, that work on the member data and are declared within the class. C doesn't permit declaring functions in a struct, but you can get a similar effect via the kind of functions that are provided in our list.h, each of which takes a list pointer as its first parameter, as you can see here. These functions use the list that you pass via that pointer as the object of their operations, and they update its fields to reflect changes resulting from the operation. For instance, list add might modify the list arrow head pointer to point to a new node. This type of design is how one does object-oriented, quote-unquote, programming in C. You declare a struct type that has all the fields needed for the data structure, and functions that accept as their first parameter a pointer to the struct that they operate on. Translating that into OO speak, the C struct type is a class with only member data, and the functions are methods that are explicitly passed their object. This is actually how things work under the hood, by the way, even in an OO language like Java or C++. Methods in those languages have an extra first parameter silently and invisibly added to them to point to the object that they're supposed to work on. You'll encounter well-organized C programs that follow the design patterns we just described, dating as far back as the 1970s. These were the forerunners of object-oriented design, and modern OO languages evolved to support these design patterns that proved useful in earlier languages. Now, several of the functions in list.h have obvious purposes. List.getCount, for instance, returns the number of integers that are presently in the list, or a number of nodes. List_add adds toAdd to a list, and we'll explain this third parameter in a later segment, by the way. List_drop removes toDrop from the list and returns true or false depending on whether toDrop was on the list. The rest of them aren't so obvious. Now, we'll discuss the iterator functions down here a little later on in the next segment. But for now, let's look at list_create and list_destroy. A complex data structure usually requires initialization. For list, we need to set both the pointers head and @ to null and the count to 0. We do this in list_create on lines 10 through 13 of list.c. Let's take a look at that. Right there. Okay. So be sure you understand what that's doing. And in listMain.c, which we haven't looked at yet but is the driver for the other two, down here, we declare an array of 3 lists. And then on lines 13 through 14, we call listCreate on each of them to initialize them. In object-oriented parlance, a function that is specifically devoted to initializing a data structure is called a constructor. Object-oriented languages let you declare constructors that are called automatically, so you never forget to initialize. But the best we can get in C is an initialization function like listCreate that we run by hand. A complex data structure also sometimes needs to be cleaned up when we no longer need it. For instance, we need to free all the nodes on a list when we're done with the list. ListDestroy does this. As you can see first in list.c, on lines 15 through 23, and then on listMain's lines 33 through 34, we call listDestroy on our 3 lists before we end the program. Again, in OO parlance, a function specifically devoted to cleaning up a data structure is called a destructor. OO languages let you declare destructors that are automatically called, so you never forget to clean up your data structure. But the best we can get in C is a cleanup function like listDestroy that we run by hand. The consistent use of list prefixes for the function names, by the way, is an old-fashioned way to do what in an object-oriented language would be done with a language feature called name scoping or name spacing, called scoping, I should say, or name spacing. In a big program, it's easy for functions to accidentally get the same name, especially if there are many different developers or when code is included from many different organizations. And function names like add, create, or getCount invite such situations since they are names that multiple developers might come up with independently. Modern languages solve this by grouping function names under scopes, such as the scope of the class that declares them, or a namespace in C++ or a package in Java. 2 functions in different scopes or namespaces may have the same name without ambiguity, in the same way that 2 fields in different C structs may have the same name without ambiguity. No such name scoping is allowed in C, but we can approximate it by consistently prefixing function names with the name of the struct to which they apply, so that they will not conflict with any other function names. Even in a very large program with many other functions, it's a lot less likely that someone else will come up with list_add or list_getCount. Now let's take a little bit closer look at listMain now. It declares and initializes an array of 3 lists, as already discussed. Declare and initialize there. And then it has a loop that performs commands of 2 possible or 3 possible forms. We can do an A command to add a number to the list, and you give then the number you want to add and where you want to add it, and that then is done by a list_add call. Or we can do a D command to drop a value from a list, and again you give the list number, 0, 1, or 2, depending on which list you want from the array, and then the value you want to drop. The list number, I'm sorry, having been read up here, and then the value down here, and then you call listDrop to drop that value from that list. And then the P command prints a particular list. Again, the command and the list are read to begin with, and if the command is a P, then we do a printf of the number of elements in the list, the list_getCount call, and then this elaborate loop here, which we will talk about in more detail later, but very briefly, it iterates through the list and prints all the items in it. Now, here's an in-lecture question for you. I'm passing lists plus list as the first parameter for almost every function call, except for the original listCreate. That's kind of odd looking. Explain exactly what is passed to the function and what type it is. Coming back from a pause there, lists, of course, is the address of the first list in the lists array. And therefore lists plus list, the number, offsets to the address of the array element specified by index list. This is the address of a list object, which is just the type needed to pass to a list pointer parameter. So we're good here. Now, you probably noticed line 4 of list.h. And up there. It gives a node typedef without providing any fields at all for node. This is a forward declaration. It's a declaration that announces the existence of a type, but provides no further details. They most often occur for structs, and one creates them simply by omitting the curly brace enclosed field list. The C compiler reads this as, I'm going to have a struct node and a typedef node as well. We'll have more details on that struct later. The compiler accepts this, but allows only limited use of the type in question. A forward declaration lets you declare pointers to the type, like we do for the fields head and at in the list struct, but that's all. Any use of the type's fields, any calls of size of, declarations of actual variables of the type are not allowed with only a forward declaration. These would all require details on the forward declared type, while a pointer declaration does not. Since all we need in list.h is to declare node pointers, the forward declaration is sufficient. If you want to do more with the type, then you must repeat the struct portion with full fields, though not the typedef. And you can see this on lines 5 through 8 of list.c. Once this is done, then the node type may be used without restriction in list.c. Now, why would we do this? Because it's a good idea to minimize the amount of detail that you put into a header file. Users of a list don't need to know the details of the node type. Only the functions in list.c that work on the list need that information about the node. Indeed, the only reason to mention node at all in the header file is to declare those node pointers in the list struct. So, what's wrong with putting details in the header file? Well, there are two things. First, anytime a header changes, you must recompile all the .c files that include it, since in effect those .c files have changed as well. As you know from earlier study, it's common in large multi-file C programs to recompile only .c files that have changed since the last compilation. This makes builds much faster. Modifications to widely used headers, however, slow the build process down by forcing recompilation of most .c files. The less detail you put in the header, the less likely it is to need modification. List.h, for instance, won't change even if we change the details of node. Only list.c would change. And the second reason is that everything in a header file is publicly available, since the file must be readable in order to be included. By contrast, the content of .c files is less public and can even be hidden entirely by supplying only the compiled version of the .c file. Decades of experience in software design has proven the value of minimizing the amount of public information available about a data structure. This isn't a matter of secrecy so much as a matter of reducing the amount that another programmer must understand about a data structure and reducing the temptation to rely on a particular implementation that might change in the future. If the user of our list class doesn't even see the content of our node struct, then they won't feel any need to understand it, nor be tempted to rely on a particular node implementation that might change in the future. In more modern languages, one may declare fields of a struct or a class to be private, preventing their use outside of the code for the class. The closest one gets to this in C is removing the details of a struct from the header via a forward declaration. It would be nice to make even the list type a forward declaration, increasing the privacy of the data structure. The reason we need the full list struct in list.h is that declaring the array lists in listMain.c down here requires full information on the list fields, since this determines the size of the list elements of the array. Pointers to list, by contrast, could be declared with only a forward declaration. So here's a question then. If we want to forward declare a list, apparently we need to use only list pointers in listMain.c. So describe generally, no particular code necessarily, just a description, how you'd change lists, the array, to do this, and how you'd adjust the parameters to the function calls down here accordingly. For now, assume there is a way to get list objects dynamically allocated, and that's the subject of the next question. And coming back from a pause there, you'd need to make lists an array of list pointers, not direct list objects. And you'd pass the actual elements of lists, like lists bracket list, to the functions instead of the addresses of the elements, since the elements would already be pointers. So in this kind of mental design modification here, how do we obtain list objects to point to? We adjust listCreate to allocate a list object and to initialize it. Now, what would the prototype for listCreate look like if we relied on it both for allocating and initializing the list object? We'd no longer pass it a list object to initialize, for one thing. Rewrite the header as you think it should look in this case. And again, coming back from a pause, there are really two equally acceptable choices. We might simply return a pointer to the allocated and initialized list object, and a prototype would look like that for listCreate. Or we could pass a pointer to listCreate to be modified, thus a double pointer. Either way, we'd have a way of getting a pointer to an allocated list back out of listCreate. So, question number 4. What could we do to free the allocated lists when we're done with them without doing a free call in main? So think about adjusting the list functions themselves to accomplish this. Coming back from a pause, one good solution would be to adjust listDestroy so that it not only freed the nodes of a list that was passed to it, but also freed the list itself.